Can I just sit and get started? I think some people come in quite fast. That's 2 minutes past. I think we can start. Probably just going to end afterwards, but I think we'll just start. Good afternoon, everybody. I'm privileged to introduce Sue Harrison. She's from Professor Sue Harrison from Chemical Engineering. She's been doing research on interventions for environmental and social benefit. However, she's also the director of the Future Water Institute, which is the Center of Excellence on Water-related Research. And myself, I know we represent the department there, but the aim is also with this work to try and foster some other links in the department as well. So Sue will actually do an introduction on the Future Water Institute, and then also give some insight into her research that she's been doing in terms of pollution and mining and other related research. So I give it over to you.
Great, so thank you very much for the invitation to be here. I'm going to talk today about, I'm first going to introduce Future Water, and then I'm going to talk about wastewaters and really creating value from wastewater, which has to do with my research. I tend to wear a few hats. I hold a research chair in bioprocess engineering. I run the Center for Bioprocess Engineering up in Chemical Engineering, and then more recently the director of Future Water, as Akil has said. And so you'll see that these slides have Future Water in them, and then they also have SIBO, which is the Bioprocess Engineering Center, where a lot of the more researchy stuff that I talk about has been done. Okay, so maybe to introduce Future Water, UCT decided that they would nurture some interdisciplinary research institutes, and so each faculty was asked to put forward a proposal around what they would like to host. And EBE had been for some time looking at a Centre of Excellence in Water, and so that's what we put forward as our suggestion. And it was one of the 5 institutes that was chosen, and so we launched in September last year, and this is the cartoon which came out of our launch. Really, we focused on water scarcity and water-sensitive design as being our key focal points. So our founding principles were really around the urgency to provide capacity for the management of the water infrastructure and scarcity, and also to look at how we adapt to water scarcity, which comes through climate change, to look at building resilience in our effective governance around water, and to be innovative as to how we're going to meet let water supply meet the growing demands. So really recognizing the need for innovation in how we use water, how we design our water systems, how we treat water, so that we can maximize what we can do with the water we have and how we minimize the environmental burden that comes from how we use water. And then also to put on top of this that everything we do must be socially acceptable and sustainable. So those are our sort of our drivers for being. This slide just indicates that we are, of the 5 institutes that were created, the most across the university. We represent all 6 faculties. We represent 10 or 11 departments, growing with time. It's so we're right from political science and anthropology through to public health, economics, engineering, environmental sciences, law, etc. So I think it's really what we need to do to meet the water challenges that we're facing. And so I'm absolutely driven that this is the path to be on. I'll also say it's quite complicated because we all speak different languages. We all do things in different ways. We're putting together a big project at the moment, and which is involving all of us. And gee, we're getting stuck on dialogue and how we do things. I see Samuel smiling because I've got him in one of the working groups, and it's not easy. So we're going to learn a lot about how we do disciplinary research by being such a cross-cutting institute, which will be great fun. I thought I'd just bring out what the 4 major themes are that we're looking at in Future Water. So our first theme, they're just depicted here from my cartoon, new taps, blue-green infrastructure, adapting to change, and maximizing value. And we'll just look through each of them and what we're trying to do with them. So before we go into the specific themes, really what we're trying to do is look at ways that we can protect our ecosystems, we can mitigate water scarcity, and we can improve water quality, with the aim of those things being to provide places where people want to live and to provide sustainable, resilient, and adaptable areas. So we don't want polluted backwaters where, you know, people eke out a living on, etc. We want this to work in this integrated kind of way. And to do this, we really are going to need to embed water-sensitive design into how we set up our systems and our settlements. So originally, when we started putting this institute together, it was a lot about water-sensitive cities. And we made the decision that we weren't limiting ourselves to cities or any particular framework. We're as interested in water-sensitive chemical plants as we are to water-sensitive cities, to water-sensitive informal settlements, to water-sensitive small towns. So this is why we have the systems and settlements as our terminology, which is not the usual terminology globally, but I think represents what we need in South Africa quite well. Okay, so our first theme is new taps, and new taps is really looking at what sources of water can we use. In South Africa, we basically use surface water. We use water which we capture in dams on the surface and then supply to our towns. What about what else we can do? Seawater, surface water, groundwater, rainwater harvesting, stormwater harvesting, reuse of wastewater. So now the draft that we're dealing with at the moment has got all of this. We're all talking about it, but I can tell you when we put this together in sometime last year, we weren't all talking about reusing wastewater or what we were doing with the aquifer or any of, and so on. So it's we really have, you know, it's a rapidly developing, very topical space. So our first theme is around what can be the sources that we use to supply water to meet the demand. Our second theme is blue-green infrastructure, which is really water-sensitive design. It's how we can look for an integrated approach to being able to get our systems working in an integrated manner. So from social development through health, through economic value, how we plan, how we build our houses, how we plan our cities, how we run our rivers, etc. That's what comes into our blue-green infrastructure project or theme. Our third theme is around adapting and building resilience. It's much more around the policy of how we, and the governance of water. It's around how we communicate and how we use our water is socially acceptable or not socially acceptable, how we manage our systems, how we culturally understand how people value water and how different people value water differently, and how we create a resilience in our water systems. And then our fourth theme is maximizing value. So this is really about closing the loop in the product life, and here our product is water, and enabling us to have greater reuse, recycling, and repurposing. So we're bringing in here the ideas of resource efficiency, which is how much value can you get out of the resource you use, the rain that falls from the sky, or wherever you get your water from. Industrial ecology, which is about being able to use waste products from one process as the raw materials for the next process, and the circular economy, which is about being able to use things again and again. And so if you think about water in this way, we're saying we shouldn't simply have rainfall, capture it, put it into our taps, and then dispose of it, but we can reuse it in multiple ways, we can recover value from it, we can recover it as value, and how do we do that? And this will very much be the topic of today's discussion. So just before I move on to that, I'd like to say, so we have these four themes, and initially we thought we would set the Institute up by having little teams in each theme, and they would go down their merry way and make it happen. But we realized that these themes are so interactive that most of the time we prefer to work together. We recognize that we have these four themes, that there are four things that we really hold as important, but most of the time we find that they're very interactive with each other. Okay, so I'm going to talk for the rest of the seminar really around maximizing value, which is the area in which most of my work is. So I'm obviously not a public health person. I don't spend my time building dams. I'm not a hydrologist. I'm a process engineer who likes to think about how to use resources better, and so that's what I'm going to focus on. And this really comes from, and I think about this in terms of many resources beyond water, but it all comes from the fact that we've happily gone along and use the resources which are beyond what our Earth regenerates every year. And I'm sure you've all seen this picture many times. There we go. Which says, you know, we used to use resources, the world will regenerate the resources that we use, and it will also have a capacity to absorb the pollution that we make. And this all used to be very good, and we used up less than the world created. But as time went on, somewhere around when I was at school, we started using more than we generate. And now, if we use well over 1.5 Earths capacity to live the lives we want to live. And those of us who live the kind of life that we all live are using probably 3 or 4 times as much, and in some countries 10 or so times as much. And there's nowhere in the world where the people have what we view to be an acceptable quality of life, HDI above 0.8, and the use of resources is less than 1. So nowhere have we got it right that we can match the quality of life we think is acceptable with not using too many resources. So we've got a bit of learning to do. Okay, so that's my driving point. If you look at the ecosystem model that we have used as our industrial ecosystem, we basically take materials, fossil fuels, whatever it is, we take into our global system, and we generate energy from fossil fuels, we produce food and agricultural products, they go to the manufacturers. As we do this, we create waste. The manufacturers create waste in an open system. The consumers consume what the manufacturers make and create waste. The waste processors recycle some of this and send it back to the beginning, but you can see these arrows are very small, and create more waste. This is how our system currently works. The natural ecosystem is a closed system. It's largely is the same kind of ecosystem, but it goes round and round. So with only the sun's energy coming in, maybe a little bit else, but not really very little else. So our question has to be, how can we close our systems if we're going to get towards a sustainable way of running? Okay, so the topic that, so through creating wealth and value from waste and byproducts, we can move towards, so we need to get rid of those wastes, those red arrows going out, and begin to be able to let them be our sources of raw materials for what we need. And so I'm really going to talk about some water-centered case studies around this. And so something we got onto a few years ago, actually in SEBA, and it was coming through into Future Water with us, is a concept of a wastewater biorefinery. And maybe you've all heard about biorefineries, because we talk about, biorefineries do get talked about. So maybe we need to take as a starting point. We all know about wastewater treatment plants. They're there for a reason. And we know about biorefineries because people are trying to make bio-based chemicals from biorefineries, largely wood-based biorefineries. So what is that versus a wastewater biorefinery? So if we look at our wastewater treatment plant is accepting that we've got this dirty water over here that we need to get to an acceptable effluent that we can discharge. And we're putting in electricity and chemicals and whatever else into this plant, and we're getting out 2 products: a water which is typically good enough to discharge, not necessarily to reuse, and a sludge which we dispose of in some way. And we do this for reasons of wanting to make sure that we don't create environmental harm or health hazards. So our key aim here is to reduce our carbon content, our nitrogen, our solids, and to produce cleaner water. Often not clean enough for reuse, although it might be, but cleaner. And our drivers are human health and environmental protection. And so basically we're taking whatever carbon, nitrogen, whatever else we've got there, and throwing it to the rubbish bin to try and get water out. And then when we want carbon and nitrogen and phosphorus for other products, we go get them from fresh resources. So the biorefinery idea, the woody biorefinery idea, is to say we can take biomass and we can, through either biochemical or thermochemical processes, we can convert it into combined heat and power, electricity and heat, and we can convert it into chemicals and fuels and materials. So now, if you look at the literature, you'll see that most biorefinery literature, there's just number of papers per year, is looks at woody biomass. And really there's very little looking at what we can recover from wastewater. But you'll see that just in the last few years, there's beginning to be a bit of emphasis there. And so our philosophy here is that we want to combine wastewater treatment with biorefineries. And so the wastewater biorefinery is then centered on converting the carbon, the nitrogen, the phosphorus, whatever other useful contaminants we have in the wastewater to value-added products, while at the same time giving us clean water as a product. And so this can contribute to the bioeconomy or to the bio-based economy. It can also contribute to the industrial ecology, where we're using waste from one thing as the feed material for another, and cleaner production, because there's going to be less waste going out. We all know it must also be economically viable. So that's really what we are focused on. So we're looking then to take the, particularly the nitrogen, the phosphorus, the carbon, and the sulfur. So carbon we know we get from biomass. Phosphorus is becoming probably our most limiting element as time goes on. And nitrogen is the most energy, we need the most energy to create combined nitrogen so we can use it for agriculture, etc. And it has one of the biggest impacts environmentally is that Haber-Bosch process to make combined nitrogen to allow us to use in other things. So in order to get these wastewater biorefineries going, we have to work at the intersection of traditional bioprocessing and wastewater treatment. And they work with quite different drivers. And so it's been quite interesting to put that together. So we're going to replace processes which are fed on pure streams. And instead we're going to use dirty streams, which therefore are non-sterile and of variable composition. And we're going to try and make the same quality products and produce clean water. That's the job. Okay, so one of the things that we've looked at to see how sensible this is to do is we've gone and looked at the different wastewaters that are available. And we classify our wastewaters in terms of their concentration, low or high, their volumes, high or low, and their complexities, which are done on these colors here. So for instance, we find municipal wastewaters, there's a huge amount of them, they're quite low concentration, whereas abattoirs are they're low volumes, but very high concentrations and very complex. In a study we did a number of years ago, quite some years ago now, we found that the organic content of wastewaters in South Africa, if we converted it into energy, would supply 10% of South Africa's electricity. So it's not trivial as to how much stuff there is around to process, but that was just being put into sludges and disposed of. And so the concept that we've tried to work with is that these wastewaters, what we want to do is to take out those different components, which are usually the organic carbon, nitrogen, and phosphorus are usually the most important ones to us. We want to make those into products, and we want to get water at the end. So we put together this biorefinery idea, and sorry, this is quite a complex diagram, where our wastewater comes in over here, and we separate out any solid. So this is actually done as treating municipal wastewater. So we'll take out the solids from municipal wastewater and take them to a biosolids fermenter, which we are still working on, which we can make products out of. Then in our first unit, we would have probably a bacterial reactor which would use up the carbon and put it, for instance, into a biopolymer. The biopolymer we've been looking at is polyglutamic acid. It's can be used as a water retention agent. So the aim would be to be able to put it into soils to let them hold the moisture better for agriculture. So we try to take a lot of carbon out at this point, and so the effluent which comes from this will still be rich in nitrogen and phosphorus. The idea is then to put that into an algal reactor over here, which would use carbon from CO2 to be able to make another set of products. So you can make algal oils for fuels, or you can make a whole lot of different algal products we can make. We're looking at algal products for fertilizers, for feeds, etc. And then from there, the water would contain small amounts of phosphorus and nitrogen and carbon. We put it into a macrophyte reactor, or wetland reactor, where you can grow plants. And you can harvest those plants as a product, so that's your next product over here. And finally, you have clean water, compliant water over here. So the idea is to be able to get all these products out as well as being able to recover your water. And so these are the systems that we are currently building up. Obviously, we also have to know that we can do this cost effectively. So one of the really interesting things in looking at wastewater treatment versus bioprocess engineering is that you have to run your reactors quite differently. So what's become really important to us is how do you select your reactor? And this is important because wastewaters are typically quite dilute, so you have to be able to put lots of liquid through your reactor without your reactor being too big. And because wastewaters are dilute, you can't afford to sterilize your incoming stream. So you have to create an environment in your reactor that will enrich for the microorganisms you want to do the job without them being the only microorganisms that you're putting in to do your bioconversion. And so that ends up needing one to think quite carefully about the reactor configuration. And this flow chart has been worked out to guide you to the right kind of reactor. And I'm not going to go into it in too much detail because I've actually got quite a lot to say today. And then we need to work out what kind of products we can recover. So the products we will recover will be ones which have an ecological niche in that reactor, so they select for themselves. And there'll also be products which are easily recoverable from a dilute aqueous stream, so preferably products which are in a different phase, a gaseous product or a solid product, so we can easily separate them without having to run complicated separation equipment with lots of chemicals. And these are some of the potential products that we can look at. So we've looked at plastics and polymers. There's a potential for renewable construction materials, composite materials, particularly from those macrophyte reactors, surfactants and biosolvents and platform chemicals and bioenergy products like methane and hydrogen are all possibilities from this. And I thought maybe it would just be interesting for a minute to look at this process flow sheet which we put together, which we put together with a group in Kenya who deal with pit sludges, and they deal with dry toilets and pit sludges. And so the aim here is to be able to look at the fecal sludge, which one's harvesting, which could also come from a waterborne sewage system. And this fecal sludge can go either to make black soldier fly, to grow black soldier flies to produce a protein product, as well as chitin, which is useful for a number of separations. The residue from the black soldier fly process can go into a composting reactor to produce compost for agriculture, or possibly some other materials. And the separated urine or the anaerobic digestion digestate, so you can produce energy in the anaerobic digestion of these kind of sludges. So either the leftover liquid from that and urine can go into another reactor where you use particularly the phosphorus and nitrogen from it to produce a whole range of different kinds of either protein products or pigments or algal products. And then out of all of this, you want to recover the water from this system. And so you end up with, from straight human waste, being able to recover a number of quite valuable products. And so this requires completely different thinking to what we've been doing before, but it's doable. And yeah. And then obviously we have to think about the economics, and the economics are going to depend on the location of the waste stream and the location of the biorefinery and what waste streams you can combine to get sufficient materials in one place at one time, the economy of scale, etc. So quite a lot of components. Okay, so this is the main concept that I wanted to introduce, was the ability to create value from straight waste resources while simultaneously looking at recovering the water as a product itself. And then I've just got two other little examples that I'd like to go through, which look at mining-related spaces. So acid mine drainage, as you all know, is a major problem in this country. So we've looked at creating value instead of acid mine drainage. So the slides here are the two forms of acid mine drainage. The one is that from water rebound from the mines, which is at very high speeds, as you can see over here, typically handled in reverse osmosis plants, which are great. They give you pure quality water, bit bank drink water from the reverse osmosis plant in that area. It's this plant down here, Kweni. The disadvantage with this is that these are brine ponds. This is where the salts are concentrated, and we just let them evaporate at the moment. And so this does give us a problem. We've still got to solve this problem. The other situations where you have seepage waters or lower rate generation of acid mine drainage And there we can look at, for instance, using biological sulfate reduction. We can use smaller scale processes to treat these waters. And what we're looking at doing there is using biological sulfate reduction. First, to convert the sulfate, which is the main component of acid mine drainage, into sulfide, and then to partially reoxidize it to biological sulfur. And then this becomes a fertilizer. So this slide just shows you the kind of complex microbial communities involved with it. But mostly I want to show you this slide where we've been looking at using a channel reactor. So furrow, what we do is we allow the anaerobic sulfate reduction bacteria to grow at the bottom of it, the aerobic sulfur forming bacteria to grow at the top of it. So we get a biofilm of sulfur on top of the reactor. This is looking down on the reactor like this, and we can harvest the sulfur product as our product, and we get clean water at the end of the day, and that water can then be reused. So this is the kind of idea we're looking at with acid mine drainage. But then looking at that, so that's all good and it's great, and we're at pilot scale with this, and there's potential that this is actually quite a desirable product. We still import sulfur into this country, it's all acid mine drainage. But the other way to think about this is why do we produce, can we not stop acid mine drainage from happening? So the other project which we've been working on, which is a bit removed from water, but the aim of it is to prevent the pollution of the water, is to say, okay, so let's stop acid mine drainage from forming. And to do that, we need to recognize, and we've done this in the context of coal, because South Africa mines a huge amount of coal. The discards typically amount to over 20% of the run-of-mine coal, which is taken from the ground, and that goes to these big piles, these big heaps, and because there's some pyrite, iron sulfide in the coal, you eventually get acid mine drainage. So how can we stop this from happening? So this just looks at South Africa's run-of-mine coal, 300 megatons a year, and this is the discards, and this is the slurry that's discarded, so what's sold is about 2/3 of what we take off the ground. So acid mine drainage will form if you have sulfide present in the presence of water and oxygen, and if you have microorganisms around, it will form faster. So one of the things we've looked at doing is saying, at least with the fine coal, is it possible to recover extra coal by a flotation stage and recover the sulfide from the coal waste which is there, and leave ourselves with a sulfide lean stream. The sulfide lean stream will then not be acid generating and will be the majority of the material that you have. So if you do these separations, if instead of only separating for the value you want, you separate to the environmentally sound place, then you can have most of your waste material not being acid generating. So this is a system that we've set up, and we have shown that we have compared this system, which is what I've just described, to what normally happens, which is just you take the water, some of the water out, and you dispose of it. You dispose of a lot of water, which then just evaporates. And we've compared them from an environmental perspective, and I'm not going to go into all of this, but just to say that when we compare things in terms of the environmental burden, we look at both the fossil depletion, land use, and water footprints as the resources. We look at the impact on climate change and acidification as the atmospheric emissions, and then we look at toxicity, salinity, and aqueous acidification, water emissions, and these are also the health issues. There's a lot of health issues around acid mine drainage and its impact on people who are living right on those dumps. And we show that in every case, our doing those extra separations will allow you to have far, so this is just done on a relative environmental burden space. I've started with the resource impacts here, the water quality impact, and you'll see all of these are far less with the separation than in the base case. The only one which isn't is that we do use more electricity, and so there is the potential for some acidification, but that comes from, but the amount that contributes to the overall process is like 1%, so it's really not important. And so we've also looked at impact of metal toxicity at the same time around this. And the metal toxicities that come from the acid mine drainage, taking the acidity will mobilize metals, like all these metals that I've got here, And that is where a lot of the health impacts come from. And you can see that we mobilize much less when we don't allow the acid to form. So there's a huge reduction in the toxicity which is created. So we like the process. What we've gone on to from there is to say, well, if we're going to do this and we're going to reduce the formation of acid mine drainage, can we also get rid of these waste products? Can we do something with the sulfide-lean tailings and with the sulfide-rich tailings, put them to other uses so that we don't have these big dumps of material? And so with the sulfide-rich tailings, we've gone through and looked at, sorry, circles to come up. We've looked at a whole lot of things that you can make out of pyrite, a whole list of different compounds. And then we've said, which of them can you make from a low-quality pyrite? And then we've gone through the processes for each of these, and we've said, and which of those would we want to make, by being able to rate them according to different criteria, and then score them according to those criteria. And the kind of criteria we've used are environmental, social, economic, and technical. So we've said things like, is this process simple enough for us to put in place easily? Is it economically viable? What is its waste generation, mineral recovery, water consumption? And is it socially going to make a difference? Will it lead to job creation? Is it safe? Will it improve community health, etc.? And out of these, we've scored each process, and we have then gone for the ones which we think are most interesting, and we have further analyzed these particular processes. And then we're doing the same thing with the sulfide-lean tailings. So we get to the stage that we can make our tailings and our discards into sorted wastes, and then we can use them for environmental benefit and economic value, which allows us then to not have the waste material and not have the environmental risk. So with the sulfide-lean tailings at the moment, we're looking at making fabricated soils. And so rather than the mine sites having to go and dig topsoil from another area of the country and truck it to rehabilitate the mine, we're taking waste coal, desulfurized waste coal, and we're making it into that soil, and we've shown we can grow grass on it, and that will eventually be our way of rehabilitating those mines. And so my concluding remarks are really quite simple. The ability to maximize value creation from resources and minimize waste burden. We're really looking to avoid the creation of waste as much as we can and repurpose the byproducts. And we need to do that before we classify them as wastes, because in South Africa's legal system, once you've classified something as a waste, you're restricted as to how you can use it. The water can serve multiple purposes before its treatment or disposal. And I think a really key concept, which hopefully came in the earlier part of this talk, is we can use water of different qualities to do different things. So you don't just need to use water once, because you can use it first and then it will become a wastewater, and then maybe it will become a wastewater, and then it will have enough things in it that you can actually use it as a raw material for a process, and then finally you can get clean water out of it and you can start the cycle again. So we need to think about what quality of water we need to do what job and how many times we can use it. And when we think about how we're going to valorize water and energy and various products, fuels and foods all become intertwined. You can create more water if you'll spend more energy, and they're all intertwined with each other, so you have to think of them as a set. I've talked about the fit-for-purpose treatments, and when we look at fit-for-purpose water, we are integrating environmental and health benefits. And so we can often use bioprocesses then to provide valuable unit operations, which they give us flexibility and adaptability, and also can often use quite complex substrates which you get in wastewaters quite effectively. And in doing this, we have to work with mixed microbial populations, we have to work with systems that handle very large volumes of water, we have to work with no sterilization before we start, and so it means we have to think about our bioprocesses completely differently, which is what we've been enjoying doing. This is my team, and people have sponsored the work over the years. So this is largely a SEBA team. This work continues on into Future Water. We've got several projects going on specific wastewaters now, and we'll start our project on the sanitation wastewater as we start next year. And then I thought I'd end by saying that Future Water will be holding its first symposium on the 28th of July, Friday the 28th of July. And for those of you who are interested in what Future Water is doing, I'd really encourage you to come and join us. We will have a morning of talks, and in the afternoon we're going to have roundtable thematic sessions. I would like to request that if you'd like to come, please do reply to Kirsty Carden. The morning is open to whoever. Many people are welcome. The afternoon we'll have a ceiling of numbers, because otherwise our round tables aren't going to work. So please do let us know if you want to be there. With that, thank you very much for your attention.
Thank you very much, sir. That was very, very interesting and very relevant the presentation. Thank you very much for that. Any questions?
So, I'm from industry, but how much are you interacting with industries to develop some of these processes?
Okay, so on the mining projects, we interact quite a lot with the industry, like with the coal mines, etc. Some of them like to hear about these ideas, some of them don't. We've been working in that space for probably close to 10 years now, and 10 years ago they hated us talking about these things, but now they like to tell me that they're doing it all already. They're doing some parts of it already. So yes, we do interact with them. On the wastewater biorefineries, we have had projects with a number of different companies. That work is largely Water Research Commission funded, and they pushed us to do a very broad study of this. So for instance, a very broad study, and now our more recent projects are focused on particular industries. So for instance, we've got a wastewater biorefinery that we're developing around the pulp and paper industry, and we're working with 2 of the companies from that industry. And so it will move on like that. So so there's scope to get much closer to the industry, but that's where we are at the moment. Yeah.
My question is also in line with that. Do you do any kind of life cycle assessment alongside your product you would like to recover?
So when I told you about the 2-stage separation to prevent acid mine drainage, that environmental burden was a life cycle assessment study. So we have to get, we use life cycle assessment a lot. So in many of our bioprocesses, we will look, if we're putting in a bioprocess because we think that it is environmentally preferable, we will use, in fact, we just about always use life cycle assessment on it. In terms of the overall wastewater biorefinery, we need to have enough data before we can meaningfully do life cycle assessment. And so we just need to get that next couple of sets of data to enable us to do that. So we haven't done it on the overall wastewater biorefinery, but we have done it on individual bioprocesses. We use it to define where we put our efforts in more research to get the processes better. We always go for the steps which are have most burden to them. And in the mining space, we are using life cycle assessment.
Is there any case study site in the Western Cape?
We don't yet have a case study site in the Western Cape around the wastewater biorefinery, but we are hoping that we will work on one of the paper mills down here. So I'm just in the process of trying to set that up. We have done quite a lot of work with the breweries on reduction of water, energy from wastewater, etc. over the years, actually for quite a lot of years now. And we're looking for sites. So if people in industry have got good sites they want us to work on, come talk to us, yeah.
Thanks. This is something I know very little about, but in the management of the waste, does that include getting the so-called endocrine disruptors out of the water?
Okay. So this is a big topic, and it's one that we aren't ourselves addressing yet. I suspect we have to go there. So we do a lot of for instance, we're doing work on anaerobic digestion from a whole lot of different sources. We're doing work with the sugar industry on sugar waste, so they come from a more defined source. So all of these anaerobic digestates, which we're now purifying up the water from, we have to look at the micropollutants on. So we've got them to a certain stage, and that's really our next step. So they come out of the anaerobic digester, we separate various things out of them, we have downstream processing from that. But the endocrine disruptors have to be our next step. And it is critical, and it's quite complicated.
I was just curious with your wastewater management, you mentioned twice you don't use any sterilization, but you obviously have some quite pathogenic bacteria sitting in there, particularly phosphorus or human wastewaters, and I'm wondering what do you do to manage that?
So in the human wastewater system, okay, let me put it like this. So in the industrial wastewater systems, you can't, in a typical bioprocess, we sterilize everything that goes into it so that we've got a nice environment to work in. And we can't do that because there's too much water to deal with and it costs too much. In the human wastewater system, well, in a wastewater treatment plant doesn't sterilize anything either. So we've got the same systems that we need to use. For instance, in that flow sheet I showed you around the fecal sludge, the step to handle that is to get your bioreactors to a high enough temperature. So you need to get them up to the upper 50s for an extended period of time to get those pathogens out. And that's the problem with all these wastewater treatment systems, is that we don't typically have a sterilization step in a wastewater treatment system. And if you want to bring the water back, you've got to think where you're going to, if the water's coming back, you're going to end up having to put it in somewhere. But then our water coming into us is mostly chlorinated or something at some point in time. So yeah, it's going to be that at that clean water stage we're going to handle that.
Okay, so
I wanted to ask you about stormwater and how viable it is to use stormwater that is discarded in Cape Town as an alternative water source, and what it would take to do that.
Okay, so my colleagues in Future Water are very much, a number of them in civil engineering, very much stormwater people. There's a lot of stormwater harvesting. How do we harvest stormwater, and how do we bring it, where do we store it, and how do we bring it back to use? There's a lot of discussion about aquifer recharge from stormwater, and then there's also all the systems around, for instance, permeable pavings, so that the water which falls actually drains down into an aquifer rather than, and through enough filtering systems, rather than running off into the sea. So stormwater harvesting is absolutely topical. There's a lot of work happening at UCT at the moment. I'm not the expert, but come talk to my colleagues.
I was just going to ask, how far down the line are these developments with biorefineries, and how long would you say it's going to take until something like this is scalable in an urban South African setting?
Okay.
And maybe part two of the question is, and what do you think should happen until that's going to happen?
Okay. So I think there's several questions, there's several answers here. So on industrial wastewaters, I think it is not that far to at least be getting energy from the wastewater and clean water. And there's systems like that. I mean, if you look at the system which has been in at the breweries for the last 10 years, the only reason why they don't put the water used as clean water is because they're nervous of public perception, because they're a beverage company. Their water is perfectly usable. In fact, at the moment, it's beginning to go onto golf courses and school fields and so on. So a lot of it's got to do with, that side has to do with our perception. But with an industrial wastewater, you know reasonably what your wastewater is going to be. And so doing this is not that difficult, and I don't think we're that far away from making these things work. The biggest difficulty there is whether the company views the wastewater, getting value from their wastewater, as core business or not, and how you handle the business case of core business versus possibly somebody else dealing with your wastewater. In terms of domestic wastewater, I think we've still got quite far to, so domestic wastewater treatment, to be able to take it right back to potable water, we can do. It's been done in Windhoek since most of my life, and Beaufort West are doing that, and it's coming through. So we can do it. But nobody's trying to get value from the water as they're doing that. And that's going to be a mindset shift. I think a big problem with that is, as our colleague asked just now, endocrine disruptors, those micropollutants that we haven't fully got our minds around yet. And I think that's going to take some time. and yet, that slide I had about the Sanitation Biorefinery, that was developed when we were with a company in Kenya who literally are doing that. They're running dry toilets, they're taking the fecal sludge, they're making it into products. They haven't got the urine side of it going yet simply because they haven't managed to organize the transport correctly yet. But it is feasible to do it, and the products meet specifications and their pathogens are gone. And so, but again, it's how do we handle a lot of it is a handling problem. So I think that is possible, but we haven't started the project on a wastewater treatment plant yet as to whether we can handle the sludge fast enough. Because one thing about human waste is there's a lot of it and it comes very fast. So your processes have to keep running, they have to be really reliable and robust because you can't have a process go slow on you. Yeah.
How much research has been done in terms of the public health impact of the pollution, in terms of the water that people are exposed to and use, things like endocrine disruptors and others? To what extent are people exposed to this and use the water, and what would be the public health, significance of?
Yeah. So again, I'm not necessarily the best person to answer this question, but my sense, and the sense I'm getting from the people that I'm working with in Future Water, is that we are exposed to, many people, not necessarily me personally, are exposed to water which has public health issues all of the time, a lot of the time. And we really need to start putting a lot of effort into how we're going to handle those systems to try and improve the public health risks of our rivers and so on. The endocrine disruptors are a big one, but also just the straight microbial contamination seems to be an issue. So yeah, I think it's one of the projects I would really like to see Future Water get into in a big way. And I think with some of the work which has been done around the water hub, which I didn't talk about, out of Franschhoek, where we've got the wastewater treatment work, Old Franschhoek wastewater treatment works to use as a testing ground, looking at streams which are coming off informal settlements, being able to, some of the work which has been done along the rivers, the Kuils River and the Lisbeth River and the other one. You guys are working on it, the name escapes me. The Lotus River. I think those kind of projects are really important, and I think we need to get quite a groundswell of research going in that kind of space. It's not what I do every day as a process engineer, but I am quite interested in how we sort out contaminant problems. Yeah. Okay.
Any other questions? Okay, then that brings us to the end of the seminar. So thank you very much for a very seminar and very interesting discussion.
Thank you, Akil.
Thanks for your input as well.
Great.
Great.
Good. I hope that was interesting enough.
Yeah,